All right, so here's the diagram for a question that we looked at last time. We were going to do a double integral over a certain region. The region is bounded by this curve and that curve. And, of course, the region then is this thing in between here. By the way, a quick aside. The term is bounded by, or, R is the region that is bounded by a couple of curves. Is bounded by means two things. For one thing, it means that it's bounded. It means that the set that we're talking about, you can put a fence around it. Right? So the other thing that it means, of course, is that the region in question, its boundary is made up of the curves in question. And you can see here that, this is the boundary of the region we're talking about, and that boundary is made up by these two curves. Right? But it is very important to remember that first part, that when we say something is bounded by, it must be bounded. So when I say the region bounded by these two curves, I don't mean this region up here. Right? Its boundary is made up of those two curves also. But it is not bounded by those two curves because it is not bounded at all. Okay, so just heads up about the terminology. Okay, so we looked at this problem last time, and looking at this region, we sliced it up, and first we looked at the range of values for x. X starts at -1, and then slices continue until we get to x equals +1. And then, for a given value of x, the range of values of y. Well, y starts at the point defined by that point, which is on this curve, which has that equation. Solve for y, right, etc. Likewise for the endpoint, it ends at this value of y, just defined by that point, which is on this curve, which has that equation. Okay. All right. So this, like I said, is from last time. The question I want to entertain now is, how come we did our x slicing first? Or sometimes I like to say we did our x slicing on the outside, because the x slicing becomes the outside integral. Right? So how come? Why x? Why didn't we do our y slicing first? Rhetorical question. So here's what it would look like if we did our y slicing first. Same region. Okay. So now there's a temptation to look at our region here. Here it is again, same region. And to say, well, look, y goes from, look, there's the first point. So y starts at 0, and then it keeps going until you get to that point where y is equal to 2. There's a very strong temptation to say that y goes from 0 to 2. See? Y, 0 to 2. So what's wrong with that? Well, nothing immediately. I mean, if you're just writing down just the bounds on y, that's actually kind of valid, right? But it's crazy problematic. You can't. This is going to be a killer way to do the problem, because think about then what are the bounds on x. So let's pick a value of y now, somewhere between 0 and 2, right? And for that value of y, what's the range of values for x? Well, let's see here. The lower bound is determined by that point, which is on this curve. Oh, wait a minute. Not always. Right? So for these values of y, yeah. For those values of y, the point that determines the lower bound on x is on that curve. But really awkwardly, for these values of y, the point that determines, for that x slice, the point that determines the starting value of x is on that curve, not the green curve. Okay, so the formula that we're going to have then for the lower bound for x is, well, it's going to be a function of y, it depends on y, but you get different formulas. You get one formula when you're on y is between 0 and 1. You get a totally different formula when you're looking at y from 1 to 2. Because the points that determine the bounds are on different curves which have different equations. Alright, so that's uncomfortable, right? And let's stretch that out to make it a little bit clearer. For these values of y, we're going to be looking at this picture, right? And then for these values of y, we're going to be looking at that picture. And the equations, well, there's the equation on which we'll solve for the x bounds for large values of y. But here's the very different equation on which we'll solve for x, the bounds on x for the lower values of y. So, I mean, this is, so, I hate to say it, but here's what you really get. Right, that integral, this innocent-looking integral that we wrote down at first, if you really want to actually put x bounds on that, you got to consider first y going from 0 to 1, and then a totally separate question, y goes from 1 to 2. Notice the formulas. The bounds on x for the low values of y come from this equation. Solving for x, of course, you solve for x, you get plus or minus square root of y. There they are. Right? Whereas, looking at the large values of y, you get these bounds for x because you're solving for x in this equation. Solve for x, and you get, let's see, plus or minus square root of 2 minus y. Which again, you see right there. So, to my original question, how come we slice the other way? Well, because this is highly undesirable, is why, right? I mean, given my choice, would I rather work out these two separate integrals, or would I rather work out, I'm moving too far, would I rather work out instead this one integral? Sorry, wrong one. Pointed the wrong one, sorry. Would I rather work out this one integral? Well, that one's clearly nicer. By the way, here's a second thing that's nice about this formula. Let's look at the bounds themselves. The bounds themselves, the outside bounds are always constants, of course, but let's look at these inner bounds. They're polynomials. That means that when I get around to doing the outside integral, those bounds, which are going to, of course, stick into the antiderivative for the inside integral, those inner bounds will be part of the outer integrand, and I'm going to have polynomials in my integrand, and I'm not scared of that at all. Polynomials are fine. No big deal, right? Whereas, let's look at this. This couple of square roots there, those are the bounds for the inside integral. They're going to be part of the integrand for the outside integral. I'm going to have square roots in my outside integrand. And I am a little scared of that. Right? That's, integrals involving square roots are weirder and uglier and sometimes just intractable. Okay, so that's a second reason to not want to do this. Now let's think through how can we avoid this little catastrophe right here. How can we avoid that catastrophe? There's different ways to think about this. I have a couple of observations that I've made here about this, and I'm just going to walk you through them. But in the context of this example here, why did we get, I ask again rhetorically, why did we get two separate integrals here? And the answer was that, well, on this range of values for y, we were on this curve, but for this range of values of y, we were on that curve. And how did this bound, this point defining the lower bound for x, how did it jump from one curve to the other curve? Well, it jumped between the two curves where the curves intersected. And where curves intersect, I'm going to forgive the sloppiness of the language here, but I'm going to say they make a corner, right? Curves intersect, so there's a corner there. Right? So, roughly speaking, when I decided that I wanted to do my y slicing first, I sliced through a corner. That's kind of a geometric way to think about the what led to these algebraic consequences. So that's the first moral of the first story. Don't slice through corners if you possibly can, right? Try to avoid slicing through corners. Because every time you slice through a corner, two bound curves are intersecting, and you're liable to have this problem where this point jumps from one curve to the other. Okay. All right. Where do these square roots come from? How come I'm dealing with square roots? And how can I avoid that in the future? Okay, well, I got square roots because, well, don't forget these square roots are telling me what x is. Why do I need to know what x is? Well, I needed to know what x is because x was the inside variable. And this is a problem because, because x in both of these equations here is what I'm going to loosely call an independent variable. Right? Y is written as a function of x. X is not written as a function of y. Y is written as a function of x. Let me say that a little bit differently. In these two equations here, I would much rather solve for y, and I really have a strong preference not to have to solve for x. Not because I can't do it, but because the resulting expressions are less desirable. Okay, so think about, as you're making your decision of which way to slice, look at the algebra that you're given in the statement of the question and ask yourself, which variable do I want to solve for? I got to pick one. You want to solve for y, you want to solve for x. Once you've decided which one you have, once you've decided which one you would like to have to solve for, make sure you do that variable on the inside. In other words, slice first with respect to the one that you don't want to have to solve for. That make sense? All right. So both of those little lessons that we learned from this example suggest not doing the differentials in that order. Okay. All right. So a couple other quick little silly examples along these lines of corners anyway. Let's suppose your domain is this shape right here, and it's preposterous. A little quadrilateral, but hypothetically, if that's your domain, notice that if I do my y slicing first, well, I start my integral there, then I slice through corners, two corners actually, but for that value of y, so I got to start a whole new integral, and then at the end, last corner is technically a corner also, but you were going to end the integral there anyway, so we don't really care. So if I slice in the y direct, if I do my y slicing first on the outside, I'm going to have two separate integrals. However, the alternative, if I do my x slicing first, I hit more corners, and so I'm going to have 1, 2, 3 separate integrals, as opposed to the alternative, which would be 1, 2 separate integrals. So take your pick. All else being equal, I'd rather do it the green way. I'd rather do my y slicing on the outside for this case. Yeah? Okay. This is a wacky looking domain. And it's another sort of not perfect scenario. If you do your x... stylus doesn't always. There we go. If you do your x slicing on the outside, well, you start there. Now you slice through a corner there, and then you end there. So you're going to have, I don't know why my stylus is doing this, 1, 2 separate integrals. And, again, it's not optimal, but whatever. Think about the outrageous alternative. Right? If you do your y slicing first, you start there, you hit corners there, but then it gets weirder because as you go up for these values of y, the x slices are going to look like that, right? Which are actually 3 separate intervals, and so you're going to have all together then one integral for the sort of the bottom part, and then you're going to have 2, 3, 4, a total of 4 separate integrals doing it this way. And it's worse. Doing it this way, doing our dy integral on the outside, right, and proceeding along Let's look for our x bounds, and let's focus our attention just on one of these little regions. Just on this one region, right? This little bell-shaped thing here. On that region, as y goes along, let's see here. I'm going to need to solve for each value of y. I'm going to need to solve for the x bounds. So I'm going to need to look at points like that, and I'm going to need to solve for x. And if you solve for x in that algebra, well, congratulations, now you've got arc cosines in your integrand. And nobody wants that, right? This is highly undesirable. Way undesirable. So definitely don't want to do that. How are we doing? Is everybody on board? Okay. So think strategically. And make your life easy on yourself. Is that a... No? I thought I saw a hand shoot up. Okay. So moving along. Okay, so we're going to start off, we're going to talk about triple integrals now. I want to segue into triple integrals with a reminder about single variable integrals and double integrals, and notice a pattern. And here's a couple of different ways to think about single variable integrals. Hopefully these are both old news. I know with great confidence you've all not only seen this, but probably seen it almost universally, right? That one way to think of single variable integrals is to think about the integral as representing, if only, that the metaphor for the integral, the way you think about integrals is that it's area under a curve. Okay. All right. And you've heard me complain and point out that, that technically this does assume that you're looking at a graph. You won't always be looking at a graph. Graphs are dimensionally expensive. You might be looking at some other kind of thing, and the graph context might just not be at all relevant to what you're doing. So, for example, what if you're being asked to compute, on this picture right here, you've got a one-dimensional rod on which you have, mass per unit length is given. It's not a constant, and you'd like to compute the total mass on that rod. Well, there's no area on this picture, right? So I've given you all that speech before. But another way then to think about a single variable integral, still a single variable integral, is that instead of thinking of the metaphor as being that integrals you should think of as area, we have instead integrals you can think of as accumulation of, I like mass because mass is a kind of it's something we all have a very visceral experience with. We all deal with mass all the time. This stuff here is made out of mass, right? And y'all have some sense of density because y'all know. There are some things that are that's heavier than it looks, right? And it's something it's just really relatable. Okay, all right. Okay, so we have these two different points of view now. Let's talk about double integrals. And you have the same kind of a choice. Right? So double integrals you can think of geometrically, I'm going to say, if you're looking at a graph, again, you won't always be. Right? But if you are looking at a graph, and if your question is compute volume under a graph surface, all those specifics and particulars, then double integral totally does that. And that's a way to think about double integrals. That was the first sort of starter warm-up problem that we did with double integrals. And recall that I quickly kind of disavowed it. Right? I pointed out that, it's useful for certain reasons, but really a better way to think about double integrals is as accumulation of stuff over a two-dimensional region. After all, double means two. Our domain is two-dimensional, evidenced by two axes for a double integral. This really makes sense. Why are we drawing a three-dimensional picture to visualize what is intrinsically a two-dimensional construction? All right. Okay. All right, so we're at a time now where it becomes really, really important. I knew I was going to mess that up. There we go. Really, really important to pay attention to these concerns. Let me zoom out one notch here. We have the kind of geometric point of view on integrals. Again, I've kind of bad-mouthed a lot. Then we have what I'm going to call a more sort of physical way to think about integrals. And this is what I'm pushing, what I want to encourage everyone to do. Okay, so aside from the reasons that I've already given you, right, graphs are not universal. Volume question, geometry questions are a tiny fraction of what we're interested in. But these are all pretty good reasons to be down on these points of view. Here's a really persuasive, I think, reason to kind of bail on the whole graph perspective, and that is, what would a triple integral mean? I mean, we haven't defined it yet, but let's just kind of notice the pattern, kind of continue along in that general direction. Here, we're looking at a graph where, output is a function of one input variable, we get a two-dimensional picture. Here, output is a function of two input variables, we get a three-dimensional picture. Following the pattern, I should look at a function whose output is a function of three input variables, and it would be a four-dimensional picture, and I can't even fake it to be able to draw that. I just can't do it. Right? I mean, I kind of had to fake it to draw the three-dimensional picture. I had to, this always kind of makes me laugh. It's like I'm trying to con you into believing that angled line is coming out of the page, right? And, you got to kind of want to see it. Right, but it's you got to do what you got to do. But it's suboptimal. But I can't even pretend. Even if you want to see it, it's practically impossible. I'm going to go ahead and say not feasible to think about a four-dimensional picture. Right, so that's a pretty darn good reason that we should not think about integrals in that way. Whereas now let's consider the alternative. Thinking about masses. Single variable integral, I get a single integral that is a single dimension. Double integral, right? Double integral, two-dimensional. What's a triple integral? Nothing spooky at all. A triple integral is an accumulation, it's a chop it up, add it up, that happens over a three-dimensional domain. And yeah, I've got to kind of, you got to work with me to you got to want to see a three-dimensional picture here as I draw it on two-dimensional paper. Suboptimal, sure, right? But doable. That's something you can visualize. And you absolutely cannot visualize such a graph. Okay, so I think this is a really big deal. Lots of students, like I say, like to, hang their hat on this for single variable integrals, and therefore kind of tend to shy away from this, and again want to hang their hat on thinking of double integrals as, come on, it's volume under a surface. You can talk about Riemann sums all you want, but that's just, mathematicians being mathematicians. Come on, double integrals are volumes, right? The point of view goes. If a student does that, then they've set themselves up for a catastrophe here, where again you just you can't do it at all. Okay. All right, so that's my little speech on that. Let's go to actually writing down triple integrals now. This is what it sort of looks like, very, very broadly, but let's write down some details. Remember the big pattern here, and I've made a huge mess on my thing here at this point, my gosh. The pattern, though, is that each one of these things, this one-dimensional rod, you chop it up into little pieces, and then you add up the resulting masses. Chop it up, add it up. Likewise here you have to chop in two different directions, but you chop it up, add it up. It's going to be the same thing for triple integrals. I just have to slice three different directions. Kind of like this. All right, so if you have a three-dimensional solid domain, and again we're going to start with the simplest kind of domain, a rectangular box. You could imagine taking this thing and slicing it like this, and then subsequently slicing it like this, and then subsequently slicing it like this, right? So is that a dicing, maybe? Cooking terminology? Dicing instead of slicing. Anyway, the point is you do all those different slices and you end up with a bunch of little boxes. And if I were interested in how some quantity, mass, again, very viscerally relatable. If I were interested in how mass accumulates inside of this aquarium, fish tank kind of a deal. How does mass accumulate in there? How does bacteria population floating inside of this fish tank, how does that add up? Well, the total is the sum of what's inside the little pieces. Mass accumulates, population accumulates. Whatever other substance you might be interested in, we've seen billions of examples of stuff that accumulates. It's going to add up by, on each little one of these, look at how much is inside that one thing, and then you add up over all of the things. Okay. Mass is density times volume. Volume is length times width times height. The pattern continues, right? This is really just like double integrals. Okay. Everybody on board? Everybody happy so far? Okay. So here's the formula we're going to write down for this kind of a Riemann sum. This Riemann sum right here. We're going to chop up our solid into three different directions. On each piece, we're going to multiply the volume times, whatever, something appropriate to the application to get what it is that's actually accumulating. If this needs to be mass, then this needs to be density. Okay. So each one of these terms, I'm then going to add up over all the pieces. Now keep in mind, we've sliced three different directions. So we're going to describe where we are in one of these pieces by three different indices. Let's go out here. I'm going to need one more. So I need to know where am I in the x direction. That index I'm going to call I. Then I need to know where I am in the y direction. That index I'm going to call j. And then I need to know where I am in the z direction. That index I'm going to call k. So it's going to be a lot of the same formulas. Y'all remember all the b minus a over n, a plus I delta x, and then we adapted that to the y-axis. C and d instead of a and b, right? J instead of I. Same deal for the z-axis. Now you've got different bounds and you've got a different index. Grand total, though, you've got three indices, I, j, and k. And so this summation is a summation over I, j, and k, all going from 1 to n. And so notice that means that there are n cubed terms in this summation, which is a little unappealing, right? But nevertheless. Okay, so huge numbers of questions can be addressed by this construction, this Riemann sum, this 3-index Riemann sum. Right? Mass accumulates just like this. Again, if you're looking at bacteria and floating around in an aquarium, that population accumulates just like this, etc. So since this expression comes up so much, we give it a name and a notation. We call it a triple integral. I think this notation's highly natural. It's analogous, same kind of deal we did with double integrals, adapted to the context. Okay. So let's compute mass. Total mass is the sum of the individual masses. Mass accumulates. Right? On each little piece, mass is density times volume. So, per our rules about integrals, this quantity on each individual piece is size times some function appropriate to the application, just like with double integrals. This is exactly the Riemann sum that we wrote above, and so therefore it is a triple integral. And so here's our sort of first development of a triple integral to compute mass. And then remember, just as we did with double integrals, it's kind of clunky to write this Riemann sum notation. We're eventually going to replace this with this anyway. So day in and day out, this is a perfectly fine development. Just make sure to remember that when you write down stuff like this, that's just shorthand. It's just notation. to represent what you're really doing, which is you're taking a limit of a summation of little finite but small pieces. Okay. Population, same deal. Honestly, I think when I wrote this next example, I think I did a Control-C, Control-V, and then I just went through and replaced all the M's with P's. I mean, it's the same thing, right? Population accumulates. On each little piece, population is size, namely volume, times some function appropriate to the application, right? It's the same exact strategy. Different physical example, but same algebraic structure. And again, integral notation, perfectly fine. Okay. Right. Let me go back several pages back to this picture. Now, we drew this when we were looking at double integrals. Right? You may recall this is what we drew. The very first thing we drew was this picture. We started the question as, hey, I want to compute a volume. When I realized what I had was a double integral, I then said, okay, well, we're really kind of computing a double integral, but the bounds only depends on the domain. Right? And then you notice that this process of slicing up the, well, in this case, volume, that process of slicing up the volume really means, you can see it right here in this picture, that we're going to look at slices in the direction of one variable. Those slices kind of cover the whole domain. And then on each individual slice, you look at the next variable, and you look at how that next variable varies over that slice, and the bounds are determined by points that are on certain curves, blah, blah, blah. And it all happens on the domain. The idea, though, is that you keep slicing up the domain. Right? First, you're slicing perpendicular to the x-axis, and then on a given slice, you are effectively slicing up on the y-axis. And you just keep slicing in every different direction until you've sliced up the whole domain. That's kind of a way to think about it. And again, that's the initial metaphor is this volume question, and then the easier way to visualize the process is, again, here's your domain. Slice up your domain. First in the x direction, and then in the y direction. Okay, so we're going to do the same thing for triple integrals. The asterisk being that I can't draw this picture. Right? I mean, again, that's, I refer you to my earlier rant about how to think about triple integrals. I can't draw a graph picture to think about a triple integral because I don't have enough dimensions. So I can't make this geometric appeal to why it is okay to just slice up the domain. I'm going to just appeal to your trust that it is, in fact, still okay. And so just, take my word for it. I'm sorry we can't give a satisfying motivation for why this is true. Other than, again, I hope you trust me. So here's the punchline, though. Yeah, here we go. Nope, sorry, next page. Here we go. The satisfying punchline is that if you're doing a triple integral over some domain, you can just slice up in each of the directions sort of one at a time, just like with double integrals. This time, of course, it's three-dimensional. You've got three different variables to do your slicing. By the way, we're going to do loads of examples to come, exactly, the details that I'm currently glossing over. So three different directions in which to slice, and therefore you get a nesting of three single variable integrals. Sometimes I call this a triple nested integral, or a triple iterated integral, more commonly. Okay. And of course you can do that slicing in whatever order you want. It doesn't really matter what order you choose. You could do Z slicing first, or not, right? You could do Y slicing first. Previously we did Y slicing second, but you could do your Y slicing first. And instead of doing the Z slicing first like I did here, I could do that Z slicing last. right? And X slicing was last here, but it's second here. Doesn't matter. Slice whatever way you want. Again, just like with double integrals. With double integrals, there's only two different choices. Here you have, if you think about the number of different ways that you can order these differentials, you have 6 different choices. So the bad news is you've got 6 choices. That's also the good news, by the way. You got 6 different choices. You got a lot of flexibility and freedom of which way, how you want to slice up the problem. Bad news is you got a lot of choices to choose from. So anyway, I think it's about your perspective. Okay, notice that the bounds go along with the variables. So recall that our domain for our integral, here we have the x shadow, the y shadow, and the z shadow on our domain. Right, this thing here is our whole domain. The bounds go along with these shadows. Right, this right here says x ranges from x1 to x2. So wherever you're doing your x slicing, those are the bounds for x. And when you, again, just like with double integrals, if you change the order of the differentials, well, of course you got to change the bounds also. And so likewise, y gets the y bounds, and z gets the z bounds. Okay. Alrighty. You can crank out those individual single variable integrals. It's just like with double integrals, just, more so. It's 3 single variable integrals instead of 2. But again, otherwise, same thing. Okay. You do still also have to worry about the integrand. So let's look at this integrand here. And there's a temptation to look at each one of these terms and think, okay, well, antiderivative of 2x is x squared, and there's a temptation to say antiderivative of 2y is y squared. It's not. We're not here doing an integral with respect to y. We are here doing an integral with respect to x. X is the variable. This inside integral we are doing on a z slice that we have fixed. Therefore, z is constant. And furthermore, on a y slice of that z slice. And so therefore, not only is z constant, but y is constant. Both y and z are constant here. And so you treat y and z as constants in the anti-differentiation. Just like with double integrals, again, just a little more so. Everybody happy? All right. And by the way, here's a picture of that. Wait, where did I put the... I guess I put that picture later. Okay, no worries. Okay, so a bunch of definitions and sort of bits and pieces. We just developed in like 3 pages all of what took us, 30 pages to develop for double integrals, right? I skipped, I didn't skip. I shortened a lot of those discussions because it's just like those things. Right. So let's now see some examples. We're going to go straight to non-rectangular domains. I think the best way to get this is just to dive right in and just notice the patterns. Notice that we're doing exactly what we did with double integrals. And just like with double integrals, we're going to look just at a domain. So let's suppose, for example, that here's our domain. I want to compute on this domain triple integral of some function. By the way, remember that whole phases thing? Phase 1, phase 2, phase 3. Let's assume phase 1 is handled. There is an application. Maybe I'm computing the mass inside of here, or maybe I'm computing the number of butterflies, or whatever. I've got some application that I've turned into a triple integral. Something has accumulated, right? And I just want to focus on that resulting triple integral. How do we turn that phase 2, how do we turn that into a triple iterated integral? And then again, I don't want to worry about phase 3 right now. Phase 3, this is phase 3 right here. It's just actually cranking out the resulting single variable integrals. Okay, so here all we're going to worry about is how do I turn this domain into an iterated integral. Okay, so we take your pick on how you want to slice. Arbitrarily, let's do our z slices first. So we need to figure out the z bounds. Just like with double integrals, the z bounds are going to come from looking at our picture and thinking about the range of values of z as I slice perpendicular to the z-axis. I get a bunch of slices that look kind of like this. Yeah, everybody see me slicing there perpendicular to the z-axis? There's the starting value of z. There's the ending value of z. We just got to write down what we know about these points. This one happens to, sometimes it's really easy. That one's the origin. I can tell you exactly what z is at the origin. It's 0. So no work required there, no problem. Okay. But more typically, looking at a point like this one, how do I identify what is the value of z at that point? Well, this tetrahedron is given as the intersection of several planes, and what geometrically I have to look at this picture and ask, which planes does this point sit on, right? Remember, with double integrals, bounds are determined by points. Points sit on curves. Here for triple integrals, points sit on surfaces. So we're going to write down every surface that we can see that this sits on and write down the resulting equations. So, for example, this plane, right? So it's on the plane y equals 0. Secondly, it is on that plane, x equals 0. Right? And lastly, it is on this plane, which is x plus y plus z equals 1. That was given in the statement of the question. Okay, so the point that we're interested in, the point that defines our upper bound for z, that point that's going to give us our upper bound for z is on all of these surfaces that have all of these equations, and since I am interested in solving for z, I need to solve for z in all of this algebra. And it's not pre-solved for us. You've got to actually do an ever so slight amount of work there. Z is 1 minus x minus y. Don't write 1 minus x minus y, because I know more than that. X and y are 0. So it's just 1. Yeah? Everybody good? You can see that right here. Z is 1. That's our upper bound. And here it is in the resulting z integral. Z goes from 0 to 1. Okay. Everybody happy? The whole rest of this section, which I think is going to take us the rest of today's class, is going to be just a bunch of different examples of this process. Right? Bounds are determined by points. Points are now no longer on curves, dimensionally, different context. Points are now on surfaces. Surfaces have equations. And now you just have more equations of more variables to solve for, but you're still then going to find which variable is it you're trying to find the bound of and solve for it to get that bound. Again, just like double integrals. Okay. All right. So, let's move it along to the next step. We have our z bounds. So I'm now going to fix a value of z. We're going to look at a specific z slice, and on that z slice, we would now like to know what is the range of values of x. We're going to try to find our x bounds. Okay, here's a fixed z slice. We're now fixed on that z slice. I'm no longer in none of this. Forget about all this stuff over there. Don't care about it. We'll get there, right? For different values of z, we will get those points, right? But right now, we're looking at just this z slice. And only on that z slice. For that z slice, I am interested in let's see, I've already forgotten. We are now looking for the range of values of x, our next integral. Okay. So, we're going to take x slices now of this z slice. And by the way, you're going to notice, if you haven't already, the 3D drawing aspect of triple integrals is heavy, right? It just is. I mean, again, think it through. We're doing triple integrals. It is intrinsically about three-dimensional solids. Understanding three-dimensional solids as they, understanding their shape. Their shape is intrinsic to what we're doing here. So it is just unavoidable. You got to be able to draw reasonably well in 3 dimensions. Now, let me criticize my own work here. That's not beautiful. This is not frameable. So you don't aim for, like if you pick up, most other textbooks have computer-generated diagrams. That's not your goal. You can't do that with a pencil. And you don't need to do that. That's the beautiful thing about it, right? What you need is a diagram which, like my diagram here, is representative and gives you the information that you need. It does not have to be one of these sort of beautiful, I want to reach out and touch it. It looks so real. They don't need that at all. Everybody on board? See what I'm saying? But you do need something that's functional. If you're not good at three-dimensional drawing, most students aren't. Right? If you're not good at it, you got to get good at it. That's something that is unavoidably going to be like I say, an unavoidable skill, a necessary skill in dealing with triple integrals, and other things we're going to do in this class. So if this is something you're not good at, there are a couple of little tricks that I've picked up along the way, and I'd be very happy to share them. How to make drawings that are surprisingly acceptable. Not good, but surprisingly acceptable. So come to my office hours, and I'll be very happy to give you the little 10-minute tutorial on how to make decent three-dimensional drawings. Okay. All right. Okay, so we're on this z slice. We're now going to do our x slicing. We're now going to therefore slice perpendicular to the x-axis. And here's what slices look like perpendicular to the x-axis. And I appeal to your sense of three-dimensional geometry, and as I must, right? I don't have an alternative here. Those x slices in green of that orange z slice, what does it look like when that little horizontal triangle gets sliced by these vertical, perpendicular to the x-axis planes? You just gotta think it through, and it's going to be little line segments like that. So on that on that z slice, x slices just look like this. They look like little horizontal line segments, perpendicular to both the x and the z axis. I'll point out. Geometric appeal. Okay, so where's the first one? Where's the last one? We got to find the bounds on x. Again, as we're going, in this x direction. There's the first slice, and I'm going to pick, for no particular reason, I'm going to pick, let's say, that point there to represent that first slice. The last slice is I'm going to represent by, there's only one point. It's that point right there. And now we just have to ask, what do we know about these points, and specifically, what are their x coordinates? Okay. Again, the first one is a freebie. This point, sitting straight over the origin. I can see that right in the picture. So x is equal to 0 there. There's really no work required on that one. Okay. But what can I say about this point? So again, this upper bound for the x integral determined by this point. What do I know about that point? Well, we've got to, as usual, start writing down what surfaces do we know that point is on. It's on that surface with equation y equals 0. Let's see, it is on this surface with equation x plus y plus z equals 1. What other surfaces do I know that this point is on? And there's a sneaky not hidden, but there's a sneaky extra third surface that this is on, and it is on our given z slice, don't forget we have fixed z. Z is constant, is only on this z slice that I'm interested in the range of values of x. And how to write the equation for this is a little awkward. The point is, that's not. It's not actually fixed because, of course, the z could be lots of different values. I'm saying that I know what z is. I'm taking z as given, and then subsequently I'm going to let it be whatever it wants to be. Right? So the way I'm going to write this down is I'm just going to say z equals z, and again, that's lame, right? But I'm going to write it like that because that's, I think, suggestive of z is known. So if you'd prefer, you could also say z is known, fixed. Suit yourself. And now, again, we're looking for an x bound, so we need to solve for x in this equation. There's x, and I got to solve for that x. In that one equation, x is, well, let's see, it's 1 minus y minus z. But wait a minute, y is 0. And z, I don't have to get rid of z because z is known. And I just get then 1 minus z. Everybody on board? Okay. Cool. Alrighty. Moving along. So here we go. We agreed that the x, the lower bound for x was 0. With the upper bound, we just found 1 minus z. Okay. All right. Now, finally, we're still on our z slice. We then have further now, having found the range of values of x, we are now going to fix a value of x also. So we're going to look on that x slice of that z slice. On this x slice of this z slice, both x and z are known. Let me go ahead and get that out of the way. First, z is what it is, and x is what it is. And now looking at this last slice, let's see here. What else can I say about this point that determines my lower bound for y, and this point that determines my upper bound for y? Okay, well, again, the first one is freebie, right? That lower bound for y, it's clearly in, again, just looking at the geometry of the picture, that's clearly in the xz plane. Y1 is clearly 0. You don't have to really give there's not much to say to justify that. I would just write that down, that's fine. Okay. The upper, what did I just do? The upper bound, of course. Different. This upper bound for y. How am I going to find y2? Well, I got to write down what I know about that point. I know that, and I know that. Last thing that I know about that point, well, it's on that plane that still has this equation. I'm still looking to solve for y. So solve for y. Oh, that makes pluses look like minuses, doesn't it? I need to solve for y in there, and not hard to see, you get 1 minus x minus z. And again, you don't have to or / can't eliminate the x's and the z's because they are fixed. Fixed variables, right? Further to the outside variables. How are we doing? Everybody happy? Right. Yeah. So the y bounds are 0 to 1 minus x minus z. And here you go. We've done phase 2. We have turned, there was some application that gave us a triple integral. We have now turned that triple integral into an iterated integral. And now it's just phase 3 is just plug and chug. You got 3 single variable integrals to compute. Keep carefully in mind what's a variable, what's a constant throughout those calculations. But there you go. All right, and just as a reminder, I think this is where I have this extra diagram here. Yeah, so when you have a triple iterated integral for the inside integral, keep in mind that inside integral comes from, we've already decided to pick some value of z on which we then found the range of values of y. Then we subsequently fixed a value of y. So y and z are constants for the purposes of that inside integral. So we treat them as constants in the anti-differentiation. Okay. Analogously, when it comes time to doing the second integral, the middle integral, if you want to call it that, for that y integral, it remains that z is still constant, right? It's on that z slice that we're looking at the range of values of y. So z is a constant. There are no x's inside of that y integral. Those x's already integrated out. And then the last one, of course, is the freebie, the z integral. There's just the one variable, function of z. It's a variable. X's and y's are gone. They've integrated out. Okay, so the shorthand rule for this is whichever integral you might be looking at, variables that are further to the outside are to be treated as constants. Nice little shorthand way to remember as you're going through phase 3, as you're integrating out these single variable integrals. Variables that are further to the outside, treat them as constants because they are constants. Okay, bunch more slicing to do. I've got a bunch of examples. I'm mostly going to point to the pictures because the result, we've talked about the algebra a fair amount at this point. I think the algebra is pretty straightforward. So let's look at at the unit ball. This is a classic, early example for triple integrals. If we want to do this solid three-dimensional unit ball. Oh, wrong color. Suppose I do my x slicing first. Well, it's a unit ball, so it's negative 1 to 1 because it's a unit ball, right? So again, the symmetries of the unit ball are beautiful and pretty straightforward to see those bounds. So x goes from negative 1 to 1. X, negative 1 to 1. Okay, now here's where it gets a little weird. For x somewhere between negative 1 and 1, we're going to fix a value of x. We're going to look at a slice, a slice perpendicular to the x-axis, representing that particular fixed value of x. We now focus our attention just on that x slice. And moving on to the next variables, let's see, what variable did I choose? Z. Moving on to the next variables, it is only on this x slice that I want to know what is the range of values of z. So I'm not interested in the North Pole. The North Pole is not on this slice. The North Pole is on a different slice with different value of x. We'll get to the North Pole, right? But for this slice that we're looking at, we're not interested in the North Pole, and likewise, we're not interested in the South Pole, and we're not interested in what's going on way over here. Okay, so on this x slice, what do z slices look like? Now, again, I appeal to your geometric intuition, and I wish there were a different way to think about this, but there really is not a good sort of other way. Slices perpendicular to the z-axis. What do you get when you take a ball like this? Right? You've taken a slice perpendicular to the x-axis, and then on that slice, you're going to slice perpendicular to the z-axis, and you get little slices like that, I claim. Yeah. By the way, I'll mention here visualization tool that you can use is you can go to the grocery store and buy a sack of oranges and slice it up. Most people should probably eat more oranges anyway. All right. But it's surprisingly useful. I mean, I've done this a bunch of times. You take an orange, right, and as you slice through it, you just look and say, oh, Yeah, the slice, that's clearly a disc, right? You could even then take make a sort of a sliver slice there, and then take that slice and then think in terms of as you were to cut vertically, as you were to cut perpendicular to the z-axis, what those slices look like, and it just really becomes a lot easier to visualize this kind of stuff. So anyway, don't be shy about making yourself, hey, maybe you want to use modeling clay instead of oranges where it's less messy, right? But don't be shy about using visual aids as you're trying to kind of get used to this process. Obviously, no oranges allowed on the exam, right? But I think it's a good way to, once you've sliced up enough oranges, you'll start to kind of develop a memory experience of how these slicing processes go down. It really helps you build up that skill. Okay. Alrighty, so our Z slicing, again, here we go. We're focused on this, wrong color, tap. Focused on this X slice at that value of X, on which, as we slice perpendicular to the Z-axis, we get slices that look like this. And the first one is down there. The last one is up here. How do I find the Z bounds? Right? What is that point and what is that point? And it's a lot of the same stuff. There is a nice trick in this example, which is let's get to actually describing what I know about these points. Let's look at the lower point here. What is that coordinate? What do I know about this point? Well, I know a couple of things. For one thing, it's on the sphere. And so I know that x squared plus y squared plus z squared is 1. Right. I know what x is. It's on my x slice. What else do I know? Do I know anything about y on these points? And here's the where we kind of get lucky in this case. I do know something about y. And it's because I know a lot of stuff about spheres. Spheres have crazy symmetries. They're just symmetric in almost any which way you can think about. Right? And so again, I appeal to your geometric intuition. A slice perpendicular to the x-axis, if I want to know the lowest point, namely the smallest value of z, that lowest point on an x slice happens where y is equal to 0. So it's, you might say on, I wanted to be that later. It is on the xz plane. And that's just a geometric appeal to symmetries that we understand about spheres. We really have to capitalize on that symmetry in this case. If you were dealing with not a sphere, but some random lumpy shape, you'd have a hard problem on your hands to figure out how to rewrite that z bound. Lucky break. Spheres are symmetric. Y is 0. And you can take it from there and see what your z bounds are. So again, we're interested in the z bound, so we solve for z. Z is a function of x, of course, because x is known. Y is 0. Throw away the y's, and you get plus or minus square root of 1 minus x squared. And there's that z bound, the z bound plus or minus square root of 1 minus x squared. How are we doing? Is everybody on board? Different geometry, very different geometry. The pattern, right? The strategies, still the same. Okay. Alrighty. Continuing. What are the y bounds? Well, so, we still have, x is still fixed. We're still on this disk. Z is now fixed and chosen. So z and x having been fixed, we're now entirely on this slice of a slice. And again, just think about what happens when you slice perpendicular to two different axes. Okay? You're going to get a little twig parallel to the remaining axis. What are the bounds? Well, I need to know, to get this lower bound, I need to understand that point. What do I know about that point? That point I know a lot about. That point, on the one hand, that point's on the sphere. That sphere has this equation. What else do I know about that point? Well, I know what z is. I know what x is. Again, we're looking for y bounds, so solve for y. And you get plus or minus square root of 1 minus x squared minus z squared. Which is, yeah, here you go, y bounds are there. Everybody happy? Yep.
So for different shapes, are x and y, or I guess in this case, are x and z going to be fixed, or like, do they have to be fixed for us to keep moving on?
Yeah, that's right. So the general process is, look at the outside variable first.
Right.
Whatever that outside variable is, find the bounds and then fix it, and then move on to the next variable. Move on, to the next inside.
Okay.
Yeah. So fixing the outside variable is critically part of that process. And again, I'm just ripping that off from the double integrals process. Yeah. Right. Okay. Alrighty. So here's another one. Let's suppose that my domain is bounded. Now there's that terminology again. It's going to be bounded by a couple of surfaces. The surfaces are a couple of paraboloids, and I have z equals 2x squared plus 2y squared. I refer you to chapter 2. Remind yourself what that thing looks like. Right? It's sort of a stretched out standard paraboloid. Right? And then I have z equals 1 plus x squared plus y squared. Now that's another paraboloid. This one's not stretched out, but it is sort of shifted, lifted up. Okay. So our domain looks like this. There's those two paraboloids. This is our domain for a triple integral. Now again, maybe we're computing mass, maybe we're computing butterflies, right? Who cares? We've got a volume. There's some application that has resulted in a triple integral. I want to study that triple integral. Right. So, the purpose of this example, one of the main purposes of this example, is to start the conversation of how do you decide which way to slice. And again, you have a lot to choose from. You have 6 different choices. It's a lot to choose from. And just like with double integrals, things can go terribly wrong. If you make a poor choice, right, then you're going to be in this nightmarish situation. So I want to talk about the possibility here of what if we did our z slicing first. Let's just say your z slicing. And it seems fine to start. Our slices are looking like that. But then once you hit that vertex there, everything becomes very different, right? Below the vertex, everything's fine. You're getting nice little disc cross sections. Nobody's afraid of that. But then above the vertex, you get these washers. And now, you could say, okay, yeah, so what? Well, the so what is what happens when you then go on to having to slice up the washers. And let's think, for example, about what would Y slices look like. Well, we'd have a kind of a shape here. And then we hit the inner hull, and we'd have, a piece there, and then we'd have a completely different piece up there, and then lastly we'd have this piece here. So you'd have 4 separate integrals. Again, big bad idea. Nobody wants to do that, right? So doing our z slicing first is catastrophic. You can see that from the picture. Just again, look at the picture, think about what your slices look like, think about how you're going to slice up those slices. Okay. All right, now here's the next observation I want to make, and I think this is a really clever idea. Sometimes you don't even need to actually draw the slices. Sometimes You can avoid. Sometimes you can kind of leapfrog over one of the steps. It's going to kind of seem like I'm going to figure out the x and y bounds all at once without drawing either. Here's the big idea. Well, I'm going to for motivational purposes. But here's what a x slice would look like. Going in the x direction, an x slice. Oh man. As I slice through this, I'm cutting through kind of that inside paraboloid, but I'm also cutting through the outside paraboloid. Oh man, these slices are going to be tough to draw, but a x slice would look something like this. Right? For some value of x down there. That's highly undesirable. Right? Okay. Here's the way to bypass this problem. Notice that if for every point in this solid, let's say coordinates x, y, z, if I look at the projection down into the xy plane, the coordinates of that projection are going to be x, y, 0. And projection, of course, just means I'm throwing away the z coordinate. Right? So z is 0. Right? But more importantly, projection means that the xy coordinates don't change. A vertical projection, it's vertical. X doesn't change, y doesn't change. So if I think in terms of projecting the entire solid, I get this fantastic conclusion that the range of values of x and y over this solid, all the possible values of x and y on this solid, I can see all of them just by looking at the range of values of x and y on this on its shadow, on its projection down here. So, said differently, if you're, as we're going through and thinking about what's the range of values of x, what's the range of values of y, doing our x slicing and our y slicing, don't slice up the solid, slice up the shadow. And it has the same range of values of x and y. Right? So this is a big, big trick. If, now of course, you've got to assume that everything works out nicely. It has to be the case, if I want the resulting integral to make any sense, that for a given value of x and y, there needs to be, there's a lower bound and an upper bound for z, and there can't be any sort of funny business of like multiple sort of, chunks up there or anything like that. It has to be a nice, nice kind of a deal. But that being the case, this works just fine. So, ignoring then this great big ugly solid that I have a hard time drawing, let's look just at this projection down here. That projection is defined by this kind of lip of the solid. That lip is where the one surface and the other surface intersect and therefore have the same value of z, and therefore these two things are equal, and solve for, do a little bit of algebra there, and you can persuade yourself that x squared plus y squared is equal to 1. So that's that intersection. And that's the unit disk. And the range of values of x and y on the unit disk, easy. Here we go. X and y on the unit disk. Bam. Everybody on board? I didn't have to draw any of the x slices that were going to be really hard to draw well. Forget well, right? It was going to be really hard to even draw them competently, right? Acceptably. And we don't have to, because once we've chosen the first two variables, we can then choose instead to look at the projection into the corresponding coordinate plane, and we're 2/3 of the way there already. Okay, last little step. Oh gosh, let me just finish this last little bit super quick. The range of values of z, once x and y are fixed, the z bounds just come from looking at the corresponding equations. And those z-bounds give us the resulting integral, which is this. Okay, all right. Sorry, I went a couple minutes over there, so we'll draw the line right here. Pick up here on tomorrow. See y'all later. Oh, and I have homeworks to return if you'll stick around for just a moment.